We are the Aerial Robotics Club at NC State. Our development team this year has been hard at work creating this year's UAV, Aquila 3. On the flight line, this is our competition team. This is Gray, our safety pilot, Hailey, our autopilot lead, and Ethan, our ground control lead. Aquila 3 is a fixed-wing, gas-powered UAV, and its various separate modules allow for rapid prototyping and testing. Thrust is provided by a 30cc, two-stroke gas engine. The plane is in a pusher configuration with twin tail booms and a wingspan of 8 feet. Fully loaded, it weighs 33 pounds and it flies at a cruising speed of 55 knots. Aquila is manufactured using light ply for its fuselage, carbon fiber composite empennages, and a variety of other materials including birch, balsa, and 3D printed parts for our other components. The payload is 5 standard-sized, 16.5 fluid-ounce water bottles. Aquila's drop module has 5 drop tubes that each correspond to a specific target. A linear actuator is automatically retracted when we are over our drop point, which allows a pin door on the bottom side of the drop tube to slide open. We performed inverse kinematics in order to determine the drop delay and the optimal location of a drop point with respect to our target.
We use both a 5 GHz dish and 900 MHz antennas to communicate with Aquila from the ground station. Here's a block diagram of our communication system. Images are downloaded via the 5 GHz connection, while telemetry data is transmitted over 900 MHz.
We use Mission Planner and ArduPilot version 4.3.5 as our autopilot system. Within our ground control station, our autopilot engineer uses waypoint paths to control the flight path and drop locations of Aquila. For static obstacles, a waypoint course will be created that has Aquila travel around the obstacles. When dynamic obstacles are identified, the autopilot lead will edit the waypoint course in real time to avoid the dynamic obstacle. Aquila consists of an in-house fuselage made from laser-cut light ply. The wings and their control surfaces, along with the horizontal stabilizer and elevators, are created from wood and covered with ultracoat. Off-the-shelf parts are also used, such as our carbon fiber tail booms and vertical stabilizers. We use a 30cc, two-stroke gasoline-powered engine and a 19x8 wooden propeller as the plane's propulsion system. We considered many alternative designs across our manufacturing process. A drop module designed to fit on the wings and outside the fuselage was originally planned to be used. We also considered creating a multi-rotor, but found our fixed-wing design to be better suited for the mission due to the length of the waypoint course. Parafoils were considered for dropping each water bottle, but were scrapped in favor of regular parachutes. We compared the mileage of our gas engine versus an electric engine and decided to continue making our UAV gas-powered. Originally, we used a Lucid Vision camera for imagery, but swapped it out for a GoPro to reduce the complexity of camera setting adjustment. Many of our alternatives were considered, but were disregarded, as we preferred to keep our UAV system simple and with many quality of life improvements and ease of access this year.
Image testing was performed on the ground and in the air at 3 different altitudes: 100, 150, and 200 feet AGL. Aquila's imaging abilities are expected to take photos of the target from 150 feet with a resolution of 5.3K at 30 frames per second. Our ground station is expected to operate with an estimated maximum range of 18 miles running at 1 megabytes throughput. We expect a 1% packet loss. Test parameters for drop are number of parachutes, size, height, mounting, and external damping. Parachute numbers vary between 1, 2, and 3 chutes, with radii ranging between 9 and 12 inches. Drop heights were performed at 100, 150, and 200 feet. The lower the altitude, the smaller the target area. However, the payload needs airtime to properly deploy the parachutes for a safe landing. A drop height at 150 feet is chosen for aircraft and payload safety. An autonomous drop point is chosen over a known target location. The average precision of a cluster was within 10 feet. After landing, the drop location is measured using a 100-foot measuring tape. During testing, we dropped out of Aquila a total of 11 times, dropping 31 bottles and safely delivering 27 of these, and target accuracy being 30 feet. Pre-flight safety briefs are given before any mission detailing the test outline. Hardware inspections are performed before the aircraft is approved for takeoff. Weight and balance is checked to ensure the CG of the UAS is within stability margins, in front of the neutral point. Our aircraft is tested at the Wayne Miniature Aeronautics Flying Field, with a runway being 700 feet long. Aquila can take off in 300 feet and lands in 450 feet under full loading. Sharp maneuvers are performed to stress the structure of the airframe, and G-loading is recorded. For example, at a turning radius of 125 feet, the airframe experiences 3 Gs, or about 100 pounds of wing loading. Endurance flights are used to test the aircraft's capability of maintaining flight for over 12 miles. These are performed manually and autonomously, with flight time and distance traveled being measured via mission planner. Across all of our flight tests, we achieved a total of 21 flights, totaling 2 hours, 4 minutes, and 13 seconds of flight time. All flights are screen recorded on Mission Planner for post-flight analysis. The autopilot operator monitors waypoint accuracy and modifies flight plans. Of the 21 flights, 15 were partially or fully autonomous, for a total of 51 minutes and 10 seconds of autonomous flight time. The average time spent in manual mode during a mission is 2 minutes and 10 seconds. Our mission demonstration tests show that our aircraft can maintain autonomous flight greater than 12 miles in length, is able to autonomously drop 5 water bottles with an average drop accuracy of about 50% within the target, keeping it landed safely within a 600-foot runway. The average mission time for completion is 21 minutes. We conservatively expect to drop 2 bottles within 15 feet of the target in competition, for an expected score of 20% out of 50% for the drop element. We will have 3 operators of the flight line, for 25% out of 30% for the operator score. Our first proof of safe flight video is a demonstration of full manual control. The safety pilot manually takes off with the fully loaded aircraft and guides it at least 1,000 feet away from the operator. Here, the aircraft is at least 1,000 feet away from the pilot, and the task is complete. The pilot then returns into a pattern and lands the aircraft. Safety Flight Number 2, Autonomous Command. The second proof of safe flight video is a demonstration of autonomous capabilities, transitioning from manual to autonomous flight. Here, the aircraft is switched into autonomous mode as it hits its first waypoint. After completing the loop at least 200 feet away from the pilot, manual command is returned and the aircraft is landed.
Alright, it's my aircraft.
Safety Flight Number 3, Autonomous 12 Mile. The last proof of safe flight video is a demonstration of extended autonomous capabilities, the goal of which is to prove the aircraft can satisfy all flight performance requirements for the mission, such as an autonomous flight path greater than 12 miles. Here, once again, the aircraft transitions into autonomous mode. It now enters into a loiter cycle until 12 miles is traveled by the aircraft.
On the far end,
Now, the aircraft is switched into manual control, and the pilot begins to maneuver into a landing pattern mode. Tequila is now grounded. Proof of safe flight is complete. Thank you for watching our flight readiness review video. We hope to see you at our next competition at the flight line.